My name is Yuchi Higuchi, working at NAOJ and Kinda University. So at the first, I appreciate for giving the chance to introduce my recent work. This work is based. This talk is based on my recent work published in 2020, collaborating with Paula and these collaborators. So this is an outline of this talk. So at first, I briefly introduced the what is a supercluster and Shapley superclusters. And after that, I introduced the data. Maybe people knows well, but I briefly introduced that thing. And after that, I introduced what is a weak lensing. In this talk, we use the weak lensing method to analyze the data. So maybe most of people don't know the weak lensing, so I introduced that method. And next, I introduced our result, and then I will conclude the discussions. Okay, so okay, maybe people knows what is a supercluster. So supercluster is one of the largest structures in the universe. So this is the Shapley clusters. So and this size is 3.5 megaparsec. So as you can see, the supercluster is very large scale structures, and there are so many clusters in a supercluster. So we call this the supercluster is constituted from the group of the clusters, and this system is still collapsing and merging. So it means the supercluster is still growing. So there is we want to know the so this is growing. So we want to know how the supercluster affect the evolution of the galaxies and the galaxy clusters, and we want to know that how is mass distributed. So it means that if we observe the superclusters, we can only observe the baryon distributions such as galaxies and stars. So we don't know the how dark matter distributed. So in this talk, in this study, we want to know the dark matter distribution without any assumptions. So this is so in order to characterize the growth of the clusters, some of the people studied the superclusters in a simulation. This one is a study from the Duffy et al. Horizontal line axis shows the concentration. Concentration is defined as like this, and the vertical axis is the number of halos. They divided the sample into two. One is the relaxed clusters, and one is the old clusters. And they studied they measured the concentration like this. So, and they measured the result is like this. So they divided the sample into the some beings, and by using their masses, and they measure for that samples, they measure the concentration. Okay, so these lines, the difference of these lines are redshift. So please see only one lines. So red dot line shows the result for the relaxed samples, and solid line is for all samples. So as you can see, so mass concentration relation for unrelaxed sample is lower than that for the relaxed clusters. But so this one is just a result in a simulation. So we want to know whether this one is truly happen in a actual universe or not. So through our observation, we want to know, we want to confirm this result is truly true or not. Okay. And okay, as I have already noticed, if we observe the clusters, we can only object which emit lights. So, and if we want to know the dark matter distribution, in a general method, we assume galaxy bias to estimate masses, dark matter masses, like this. This one is baryon density contrast. The density contrast is defined as like this. And B is the galaxy bias, and delta is the dark matter density contrast. So we can just observe this value, and we cannot observe this one. So we just assume some value from by assuming some, we just assume some galaxy bias by using the simulation or analytical models. Then we can estimate the dark matter distribution. But this one includes some uncertainties. So, and this one causes some errors in estimation. So we need to estimate that in order to get the accurate dark matter distribution, we need to estimate the unbiased mass distribution by using some other method. Okay, so through our studies, we want to map dark matter distribution with weak ranging, and after that, we can get the weak ranging masses. So we want to compare weak ranging masses with masses estimated by other methods, and we want to confirm the mass concentration of the clusters in the supercluster. Okay. So maybe people will note this survey. So Paula proposed to observe the Shapley supercluster by using VSD, and so VSD, and this one is called as Shapley supercluster survey, which is held between 2020 to 2017. So they observed 23 square degrees, and this one is a result. So the observation includes the central 11 clusters in a Shapley supercluster, and so the median seeing is about 0.6 arcsecond, and we can use but we can also use the spectroscopic data. Okay, so for now, I briefly introduced what weak lensing is and our method in weak lensing analysis. So maybe people know the gravitational lensing effect. So the light emitted by the background galaxies is bended by the lens, this one, and so if there is a density, gravitational lensing can trace the density contrast. That gravitational lensing is sensitive to the density contrast of the lens. So that density contrast bend the lights emitted from the background galaxy, and we can see that effect by using the observation. So by using the weak lensing, we can estimate the dark matter masses without any assumption. I mean, we don't need to if we observe the baryonic matter, then we need to use the galaxy bias. But if we use weak lensing, we don't need to assume any galaxy bias. So weak lensing is an unbiased method to estimate the galaxy some lens masses. Okay, so this is the merit of the advantage of the weak lensing. So I want to briefly introduce the weak lensing and how to estimate the weak lensing effect. So if this one is the result from the Hubble Space Telescope. So weak lensing is a very weak effect. So in this photo, we can see some arcs like this and like this, but this one is the strong lensing effect. So in a weak lensing effect, the effect is very weak. And the galaxy shape is skewed about a few percent. So it's quite hard to measure the effect from only from the observation for the one object. So we need to carry out the statistical analysis. So okay, so we just observe the many galaxies and galaxy shapes and take ensemble averages, then we can get the weak lensing effect. So I want to briefly introduce such method. This one is the observed galaxy shapes. So we can only know this value, but if there is a weak lensing effect, this value is this one is consists from of the two components. One is intrinsic galaxy shapes, and one is one is a gravitational lensing effect, which this one is called as the shear. So this one means that observed galaxy shapes is a sum of the intrinsic galaxy shapes and gravitational lensing effect. So, but if we only observe one object, we cannot distinguish two components, this one and this one. So we need to take ensemble average and some assumption, one assumption. The assumption is like this: in the universe there is no particular direction and the positions. It means if we take ensemble averages for this one, then if there is no particular directions and positions, then if we take ensemble average, this value becomes 0. So if we take ensemble average, then the ensemble average of the observed galaxy shapes becomes the gravitational lensing effect. So this one is the basics of the weak lensing. And okay, and if there is some gravitational lensing effect, then the galaxy shapes becomes like this. And this one shows that if there is one cluster on the center, then the galaxy is skewed like tangentially. And this one is called as tangential shear. And there is another component. This one is called as a B mode cross shear. And this one theoretically this one becomes 0, but if there is some systematics or then this one doesn't become 0. So if this value is used for the check of the systematics. So okay, I want to show one simple example. This one is done by Umetsu 2014, and they use the 16 X-ray selected clusters, and they use the clusters present in between the redshift range of the 0.2 and 0.7, and they measured the tangential shear for 16 clusters at each beams, radial beams, and they stack the lensing signal. Then this one is the result. This top panel shows that this one shows the tangential shear. On the other hand, this one shows the B mode. So as you can see, if we observe the clusters, then we can measure the shear, and this shear is fitted by the NFW, and they estimated the mass like this. And as you can see, if there is no systematics, then the bib mode becomes like 0. So by using the weak lensing, we don't need to assume galaxy bias, and we can get the unbiased cluster mass by using the weak lensing. So okay. So and as I have already said, we can only measure the galaxy shapes, but in order to estimate the mass, then we need to convert the galaxy shapes to from galaxy shapes to mass, and okay. So in a gravitational lensing, there is a relation between the mass and shear. So we use the this relation. So this one is, we can observe only shear, but there is a relation between the shear and mass. So we can convert shear from shear to mass. So we can make a mass map from the shear value. So this one is one example for the mass map. This one is a result from the Subaru Hyper Supreme Com survey. This one is a studied in Ogri et al. And top panel shows the weak lensing mass map, and the bottom panel shows the galaxy density map. As you can see, there is a tight correlation between two. Like, for example, here there is some masses, and in a lower panel, we can also see a mass in a galaxy density map. So if we use the weak lensing mass, then we can get the mass map. Okay, so from now, I want to briefly introduce our weak lensing analysis method. Okay, so background, in order to measure the mass by using the weak lensing, we need to use the background galaxies, because the only background galaxy is affected by a gravitational lensing effect. So we need to select the background galaxies, and if we use the galaxies behind in front of the lens, then this one causes some systematics in the weak lensing signal. So we want to exclude such galaxies and want to only select the background galaxies. So in order to do that, we just use a color diagram. This one shows the selection, and this one is the color diagram which was used in our studies, and colors means the distance between the lens and source, and this one is the distance to the source. So by using this value, we just select the background galaxy, and in order to measure the correct galaxy shape, we only use the bright galaxies, and we use the KSB method. I haven't introduced shape measurement method, but there are so many shape measurement methods. We just use one of the such methods, so which is called as KSB. So this one is okay. So we use this one, and the number density of the background galaxy becomes about 7 arc minutes. Oh, sorry, this is typo. Arc minutes. So, and the mean redshift of the background galaxy is 0.8. This one shows the result for the selection of the background galaxy. So, and if we don't use any color cut, the this one black dot shows the without any color cut, and the solid line shows the result for the result with the color cut. So as you can see, if we don't use any color cut, there is a contamination for the background galaxies like this. But if we use the color cut, then we can use only background galaxies like this. Okay. And in order to estimate the mass, as I have already told, we want to know that we want to investigate the mass and the concentration relation. And so in order to estimate such thing, we estimate these values for the clusters in the Shapley cluster. Okay. So for massive cluster, we use two methods. One is the how to say one is the result. One is the method I have already shown, and which is used in Umetsu et al. Like this. For Romas clusters, the weak lensing signal is very low, so it's quite hard to detect the weak lensing signals. So we divided the, if we pick up one sample, then we divide the samples. We divide the distance. We how to say? We use the annulus beam to measure the tangential shear like this, and we fitted this tangential shear with the NFW models by using, and in the NFW we have two parameters. One is the mass and one is concentration. So we just use there is two free parameters in this model, and in the Shapley clusters there is in total there is 11 clusters, but for 7 clusters are the low mass clusters. So we use this method for the low 7 clusters, and for high massive clusters we didn't use, we used another method. We divided the sky into cells like this, and in each cells we measured the shear, we estimated the shear, and we fitted the shear value in this plane. Okay, so this one, while for massive clusters, the weak lensing signal is very low, very high. So, and we don't need to divide the sample like this. And if we use this method, we can trace the substructures and substructures. But if we take ensemble average at each annulus beam, then the substructures is disappear. So in order to trace the substructures in clusters, we use this method for massive clusters. There are 4 massive clusters. We just use this method for 4 massive clusters. Okay, and we divide the skies into 3 arc minutes on the side, and we checked the size is not does not affect the result, and okay, and we fitted the 4 clusters with the NFW simultaneously. Okay, so this is a mass map. This is the result for the our study, and this one shows the mass map. We smooth the map with 10 arc minutes. As you can see, and the color shows the galaxy density map, and the contour shows the result from the weak lensing. So contour means the mass map from the weak lensing. As you can see, there are tight correlation between the weak lensing signals and the galaxy distribution. And we confirmed the 2 clusters behind the superclusters because the mean redshift of the background galaxy is the 0.8, so we can trace the background clusters. Okay, so we found the clusters at the redshift of the 0.17, and this one is a galaxy distribution. So if we use the weak lensing, we can trace the matter between the source and observer. Okay, and Paula found some filamentary structure in a previous paper between the this cluster and here. So the filament structure is it's quite hard to see the filamentary structure in weak lensing because the weak lensing signal from the filamentary structure is very weak. So it's quite hard to detect such thing, but we can see some filamentary structure here in a weak lensing map. So we can trace the such structure even if we use the weak lensing. Okay, so by fitting the clusters with the NFW profile, then we can get the mass from the fitting. In the fitting, we just use the we just use the 2 parameters, mass and concentration, and this one shows the result for the mass estimation. Blue one shows that, and this one is a comparison between the weak lensing mass and dynamical mass. So blue shows the result from the weak lensing. On the other hand, red shows the dynamical mass. Okay, for all clusters, the mass is the consistent within 2 sigma. So yeah, so even if we use dynamical mass, we can get the close mass, but yeah, and okay, and the total mass for the 4 clusters is like this, and this one is a result between the this one is a comparison between the different estimation method. This one is the masses from the dynamical mass. This one is the dynamical mass. So, and this one is the mass from the X-ray observation. And this one is the result from our study. It means weak lensing. So, as you can see, these results are consistent. Okay. And we also investigated the mass and concentration relation, and horizontal axis shows the mass, and the vertical axis shows the concentration. As I have already said, the weak lensing signal from the low mass clusters are very weak, so we cannot constrain on. We couldn't. It's quite hard to give a tight constraint on concentration parameter for such low mass clusters. So I just showed the result for massive clusters. And this one is the result for the massive clusters, and this line shows the result from the Duffy et al., which is the result from the simulation for the all sample. All samples. So as you can see, sorry, this one is not all sample. This one is the 4 relaxed clusters. All samples. Yeah. So as you can see, the error bar is very large, so it's quite hard to see that to confirm the result from the simulation, but we can see some the concentration for the massive cluster is lower than the simulation result. So this result might indicate the low concentration parameters for unrelaxed clusters. Okay, so we investigated the mass distribution and the galaxy. We wanted to investigate the mass distribution and the evolution of clusters in a Shapley supercluster. And we carried out the weak lensing analysis of the Shapley supercluster. And after the analysis, we compared the mass distribution between the galaxy distribution. The weak lensing mass distribution is consistent with the galaxy distribution, and we obtained the weak lensing mass by fitting with NFW, and we obtained weak lensing mass consistent with those obtained from the other analysis within 2 sigma, and we have also studied the mass concentration relation, and that result shows the low concentration parameters. Concentration parameter is consistent with those for the unrelaxed clusters obtained in a simulation. And as a future work, we want to carry out the weak lensing analysis for the wider region. This survey is only observe the central region, and we need to confirm we want to analyze other regions, and we studied the mass and concentration relation for the superclusters, and that such result is might be consistent with the simulation, but the result, the sample is only 3. So we need statistical analysis of the mass and concentration for unrelaxed clusters. So we need to increase the samples by using other surveys or observe wider areas. So this is the future work. Okay, thank you.